Today's topic, sensory motor rhythms. You have read about this in the gentle introduction to brain-computer interfaces paper. You have also presented the idea behind how brain rhythms can be modulated. As a recap, what do you know about ERD, ERS generally from your readings? Event-related desynchronization, event-related synchronization. You presented it last time, right? What is that? Or modulation of your power spectra? Yeah, exactly. Decrease or increase. SMR stands for sensory motor rhythm. Sensory relate to our sensory cortex. Okay. If you imagine left hand or right hand movement, the opposite or contralateral side of your cortex will start firing. So starting firing reflects the change in the modulation of your EEG patterns or brain rhythms. Okay? And this kind of BCI can be used to control different applications. And again, in this case, you don't have any visual stimulation or any kind of stimulation. You're just thinking to generate or to modulate your brain signals. How this happens? Okay, most rhythms are idle rhythms. For example, I said that a brain is a synchronous system, right? All the neurons are firing in synchronous manner. So the well-known rhythm or synchronous neural activity is called as alpha rhythm. So alpha rhythm is the rhythm that happens around 10 hertz. So it happens from 8 to 10 hertz, right? It's a frequency band of alpha rhythm. And that happens in your visual cortex. Okay, so our visual cortex has background synchronous activity. So visual cortex is here, right? That processes information in the brain. That's coming from our eyes. So if you close your eye, look, increase in the signal amplitude, signal power. And then when you open your eye, okay, so background rhythm breaks, and then there is suppression in the signal, in the EEG signal. We're talking about the EEG signal. Is this clear? So we have some idle state. Let's call it as this one. Close eyes. Increase in the power. When you open the eye, what happens? The decrease in the signal power happens. And that decrease in the signal is related to the information processing or your brain, visual cortex. Excuse me, what happens when you open your eye? You have visual information. That's feeding to your brain. Right? When you close your eye, you have darkness, you don't see anything. Right? So, input of the information to your brain through your eyes will break the background idle rhythm. Similarly, mu rhythm, very similar to the alpha rhythm and has same spectral properties, usually overlaps, and is around from 8 to 10 or 8 to 12. It's also a subject specific. However, the range is around 10. Okay? How this happens? And motor and sensor cortex. If alpha rhythm suppression happens in our visual cortex, we know location of motor and sensor cortex. So there are some different namings in the brain. One is sulci or sulcus and gyri. Okay, sulcus is these tracks. Okay, and gyri is its foldings. So central sulcus that separates frontal cortex from the parietal. Right before the central sulcus is motor cortex. Right after that, this defines sensor cortex. So if you place electrode on top of that area right here, around here you have seen CZ, right? And record brain activity, two conditions. In the first case, your arm is at rest. We know that motor cortex is responsible for our motions, limb movement. If your arm is at rest, you have some background synchronous activity. You start to move your arm just like this. Okay, now I'm doing nothing, right? I can detect idle rhythm in my sensomotor cortex. I'm not moving now. And if I start moving this, suppression in that signal happens. So EEG represents brain electrical activity. And that electrical activity is based on inhibitory or excitatory postsynaptic potential. And the postsynaptic potential happens when different neurons fires, right? Increase or decrease. So actually the suppression is directly related to our brain activation. Then this happens. And interesting enough, so kind of suppression not only happens when we move our arm, but also when we think about moving. And if I imagine doing that, same suppression happens on the sensomotor cortex. You just imagine of some motion, and there is pattern or the brain rhythm modulation that can be used to detect brain state. Clear? So another very widely used paradigm is so-called based on sensomotor cortex. Yeah, so locations of electrodes are here. Just one electrode, C3. There are different kinds of oscillations. One is called steady state visual evoked potentials. Also, these kind of oscillations are generated by some visual cue. And these modulations can be captured in spectral domain, not in time. ERP is in time, right? So one difference to note is that these kind of steady state visual are evoked potentials, but not the induced. Induced is what we imagine without any external stimulation. SSVP is synchronous to periodic external stimuli, while SMR, sensor motor rhythms, are asynchronous. It's not synchronous, so it's internally generated. It's not synchronous to any kind of event. This is an example of exogenous activity as ERPs, just like event-related potentials. While, the examples that we have seen, the mu rhythm modulations are endogenous activity. Right? I talked about the spectral features, and let's go some details. What's shown here is just topographic view of the scalp. For example, right hand movement modulates left side or left hemisphere. Look. And left hand movement or imagination modulates right hemisphere. Okay, so this is your left hand. If you imagine moving your left hand, we are looking for the modulations at or on the contralateral side. So this is typical or idealized spectrum of EEG. We have alpha, right, beta, and gamma, and there are some high gamma. So alpha rhythm, in ideal, in synchronous case, we have this prototypical or typical spectrum, frequency and signal power. And, this comes from cable noise, so-called, on 50 or 60 hertz interference. Assume that you imagine moving of your left hand right here. We have some color change here, right? Okay, we don't have color bar here. We can think as we do, more red means more power, blue means negative, right? Suppression. Take a look at the spectrum. Just take the data from C4 channel or estimate power spectral density and compare with the idle background. So in the previous slide, we said that this is typical background activity when you're doing nothing. Synchronous brain activities, spectral power, right? And when you just think about moving your right hand, what happens? You see the difference? In time domain, we have seen that. Yeah, how it looks like in the frequency domain is the power of the spectral power of the signal decreases, or there is suppression. Not only moving, but also imagining a movement of the limb causes a local blocking of the corresponding sensory motor rhythm. Similarly, if you imagine moving your right hand, what happens? The left hemisphere of your brain, in particular sensomotor area, will have some suppression in the spectral power. For instance, you can take this C3. And when you imagine about moving your foot or your feet, right, functional location where we can detect these patterns, CZ. In one of the classes we covered, we briefly reviewed this functional localization of different human organs to the sensomotor cortex, right? Do you remember? And we called it as homunculus map. CZ captures the leg movement. For example, if I jump, my CZ is being activated. The neurons in this area is taking responsibility to handling this activity. Coordinate. So modulation of sensomotor cortex in motor imagery from one subject when he did two tasks. He imagined about moving his left arm and right arm. And what we see here? Spectrum, right? Let me go in detail. C3 is a channel located in the left hemisphere. C4 is a channel located in right hemisphere. When you think about left hand movement, we can compare the suppression in the power, right, as compared to the right hand movement. And they are very well localized here. And when you think about right hand movement, there is very nice suppression, clear suppression, or some patterns that can be localized in the other side, like C3. Okay, so if you just plot it differently, we can see here and here, right? And that's happening around mu rhythm, so-called, around 10 hertz. We don't see the differences, strong differences in the other spectrum. Any questions? And this can be used to control external device. Two different patterns, right? That can be used as a binary command. Yes and no. However, the case was from a very nice example idealized and where we had very nice suppression. When the subject thought about moving his right arm, left arm, we had very clear suppression. However, in practice, the difference may be very small. The left and right imagination. And take one channel, CP4. What's the location of CP4? Right, yeah? Central parietal lobe. Visually, do you see any difference? No, right? They're very similar, almost overlapping each other. And the R-square metric doesn't show any differentiated discrimination. Only except this part, right? Only except this part. This we see a little bit discrimination. And one reason for that is special smearing. So special smearing has another name, so-called volume conduction effect. So volume conduction effect is the effect of our head compartments to the electrical activity. The EEG will pick up the mixed signals or electrical activities. And channels are very highly correlated to each other. right? So here, because one of the reasons is that spatial smearing, so mixing of sources from different channels. To minimize those kind of mixing, spatial mixing or spatial smearing, there are some approaches already developed. One typical, or one very simple one is bipolar spatial filter. Another one is common average reference, or the other one is Morton Laplacian filter. So how they're defined? So bipolar filter is a filter that calculates the difference between two channels and then replaces the channel with the difference. If two channels are highly correlated, by subtracting what happens, what is the effect of subtraction? We're removing common patterns. That has very simple effect on minimizing this correlation. Okay, this kind of filtering can somewhat help to improve this discrimination or discriminatory level between two channels. The common average referencing filter is simply the subtraction operation of the entire, the mean, subtract the average of all channels or electrodes from the given electrode. So here, this operation, you take the average of entire channel or electrodes. You assume you have 64 channels, right? You perform averaging, you have one resulted common average channel. What you do next is you subtract that from, for example, C3 channel. And the effect is very nice. So you do this for the entire channel. So for example, C3 was replaced by CAR, common average reference, and all others. You just iteratively just subtract all these average. Another one, more accurate, more localized common average referencing. Okay. In this case, if you have global average, in Laplacian filter, we try to make the local average and subtract. For instance, look at this. The C3 is replaced by taking the average of the neighboring channels and by subtracting C3. So new C3 left, corresponds to the following operation. So FC3, C1, CP3, and C5, C1, C5, FC3, and CP3. Okay, so it's kind of local operation. You're subtracting the local average from each channel. And you do iteratively for all that. So you take this as the next step, CP3, right, as a central channel, and you subtract the neighboring 4 channels. Is this clear? And the point of doing this is, again, to minimize the spatial mixing. So, for example, so C3 has its own time series, and we have some average information around channels, right? And that average information also contained in the C3. Okay, we are just taking the difference and then obtaining some new form of C3, common spatial patterns. It's a supervised learning method that tries to, also the data-driven method that tries to find optimal filters. However, it uses labels of 2 classes. So it's a supervised learning. Okay, now let's assume that we have done, or we have applied these 4 different types of filters to the original raw CP4 channel. When you do bipolar subtraction of FC4 and CP4, you have some small effect, right, on both channels, on both cases, left and right. Here, so R square is a metric that shows a discriminatory level of 2 class patterns. We see here some pattern, right? At this point, And when you apply common average referencing, the effect is as follows. Okay? Much better. Laplace, common average, entire global, and Laplace, local. We already see discrimination. Very simple filters, but improving the original raw data by maximizing the difference, variance of two classes. Well, the most, as I said, the state of the art, which is current state of the art, is common spatial patterns. It's a supervised learning method that tries to find this optimal spatial filters that maximizes the difference between two classes. And it has very nice effect. You see, visually very separable. And also the R-square metric shows at this point we have some, very separable patterns. Clear? So, we know the problem, spatial smearing or volume conduction effect, because each electrode picks up the activities from different areas of the brain, and that brings us very overlapping patterns. However, we can improve that by applying not temporal but spatial filter. Some comment, in order to determine the frequency band that best displays a modulation of sensor motorism, SMR, it's helpful to know approximately at which channel these are to be expected. So, frequency band. Okay, best frequency band. Here we have from 0 to 30, from 5, right? And here, which frequency band shows discriminatory activity? That's a question. 10 to 15, visually, right? We can also answer this question by empirically verifying, by taking the data from each channel and doing some classification. So, alright, so let's see. Again, it shows the topography, strengths of the local rhythm. What happened here, average topography. So, for each Laplace filter channel in a relaxed recording, the strength of local rhythm was estimated. Okay, the grand average over 80 participants is displayed as topographic mapping. 80 subjects participate in this experiment. If you average across entire subjects, we can localize the best channels. And in this case was two channels, C4, C3 and C4. So these C3 and C4 are good candidates to observe SMR modulations and discover, clear, right? Sensor motor areas. Filter channel in a motor imagery recording. The classification accuracy was determined for single channel classification. So over 80 participants. So in this experiment, the authors has taken each channel as one input to the classifier. If you have 30 channels, you run your classifier just taking one channel data and estimate accuracy. All 30 channels, you do 30 classification. And then you plot the accuracy as topo plot. And the color represents the accuracy. Clear? So, by doing this, we are answering the question, which channel carries most discriminatory information? If there is discriminatory information, we can expect that the classification accuracy could be high, right? Makes sense. 70% more red is good. So, binary classification, 30 subjects, left hand movement against right hand. 30 subjects performed that. And left, right, we have seen very good classification here, over the right hemisphere and left hand area, right? And also here, the binary classification. But these areas, showed very poor performance. Left and foot movement, 34 subjects. Again, these areas have shown very strong classification accuracy as compared to other channels located here. Also right here. And how about this? Foot and right hand movement, binary classification task. You take each individual channel, run your classifier and estimate its accuracy. Looks like this channel, only single channel, which is located here, C5, carries good information. Alright, So analysis of multi-measure conditions, again, how many channels? We have here 17 channels, right? Two class conditions are shown. Blue left. Okay, red is right. And all this has been acquired by LARs, Laplacian. Surface Laplacian filter. We have some activities. Look at this bar plot. More red means more discriminatory activity. What we can conclude from this graph is that parietal channels doesn't have any information. The central channels have some patterns for binary classification, right? Because this is the area responsible for processing that information. Alright, so first step is determine suitable frequency band that shows good discrimination between two conditions. Another question, when? Right? In time, this happens. Suppression or increase in the power spectrum. Okay, how do you obtain this, quantify this increase and decrease in signal power is tolerant, right? Let's consider the single trial. You have raw data, you identified the frequency band 10 to 15. Let's bandpass, with a cutoff frequency 10 and 15. Okay, low and high. Another one is rectification, right? You just take the square of the signal bandpass filter, and what do you see here? Some increase and decrease of signal power, some modulation. And this actually captures the power of the signal either in frequency and in time domain. However, we are considering here a time domain across trials. So let's assume that we start thinking event around this point, 3 dots. Okay, after this. Another one is what single trial, and across trials we usually report several hundred trials. And if you average all the trials, rectification form of all the trials, you may have more information. Maybe not here, and then you employ smoothing technique, and probably here some suppression, like across trials. Signal power is decreasing. Okay. Yeah. By the way, these signals are called as ERD and ERS. You presented it last time, right? Desynchronization means power reduction or suppression, and synchronization of ERS is rebound. There is even rebound back to the synchronous activity. However, that ERS is captured not in mu band, however in beta band. Let's say 25 to 30 frequency range. Here. Okay, suppression, and then here we know some increase again, right? Rebound. So event-related desynchronization, and here we are observing synchronization, event-related synchronization. And that can also be used as input to control some devices. Alright, so here what we have, ERD and ERS curves. And what we see here is time domain, not a frequency. And the time window is 2 seconds. Okay, 2000 milliseconds. Do we see any decrease in the power? After smoothing operation, right? You have done all these steps, the entire channels, entire trials. And what we see here is, again, R square represents separability from 66 subject left and right again. I don't see any very prominent power separation here, or neither here. Nor here. C1, CZ, C2, no. But however, something interesting is happening C3 and C4, right? So the power, okay, after the onset of imagination, there is a very nice decrease, right, in the power of the signal. Again, this is time domain. We are trying to identify when that power decrease happened. Right, immediately after, within the matters of 300 or 500 milliseconds. If the entire window is 2 seconds, then let's say this is 500 milliseconds. Immediately, right? C4 channel, C3 channel, carries very nice information. And yeah, CP3 has some synchronization. Decrease and then increase. And let's call it as baseline, this horizontal line. So first we identified frequency band. Next is time. When in time that suppression happens. Okay, you can calculate spatio-temporal features of event-related synchronization or desynchronization event. What do you see here? Left, right foot movements. 3 classes. Foot, right, and left. Okay? These topographic plots represent time evolution. You start before thinking, and when you think about left hand, yes, there is some modulation, some suppression. And even here, however, this is the synchronization, going back to the background synchronous activity. You don't see any suppression. Right also. In left, what do you see here? Right hemisphere has very nice modulation. When you think about right, left hemisphere has very nice modulation. Okay? And foot, where foot? It should be somewhere here. However, two hemispheres are modulated as compared to baseline. Okay, 500 milliseconds. This is average. Another one, right, and another one. So for left and foot movement. And this kind of information can be used to build a binary BCI. That advantage of this kind of BCI paradigm is that you are free. You are not constrained to excellence. You can do self-paced BCI, self-paced, independent of any external. Because we know when you think about our limb movements, there is a modulation in the brain pattern. Okay, we can just use Hilbert transform. And what does Hilbert transform do? It actually captures the envelope of the signal. We can use that and feed it as a input to the classifier. However, the mixing has effect. So usually it results in a weakly classification performance. So Hilbert transform will do same things. It captures the modulation. Instead of doing these operations, you can apply Hilbert transform and then it will give you this. Increase, decrease. So what we have learned so far is background rhythm, modulated rhythm. Modulated in a sense that there is a suppression. We can observe in alpha, beta band. In time domain, if you compare resting state, this is one channel from C4. When you start thinking, automatically what happens? Suppression. This is right, start of the right movement, left movement, okay? C3. Right should capture, C3 channel should capture right movement, right? So it's suppression because it's located on the opposite side. And C4 should capture left movement. And if you project it in this direction, all the amplitudes, here, what we will have? C3 against C4. There is very huge overlap, okay, between two classes here. The green against, by mapping, by projection, the amplitude of signals we cannot see, therefore we can just take the variance of all trials of 100, let's say, 100 trials, and then map it to this way. Again, also it shows C3 against C4. And when you take the variance captures the variance, right, between two classes. In one case, we have high variance. In this case, small variance of sampling. And this can be plotted, visualized in two dimensions like this. And what do you see here? Much better. Right? And if you just take the logarithm of this variance, each point represents one single triangle. Yeah, very nice. Kind of Gaussian distribution of two classes with the centers located here. Alright, so closer look, signals are filtered to frequency, band of interest, 10 to 15, and then what's the consequence of this one is that C4, the variance is very great for C3 and very small, again for C4. So there is a common spatial pattern algorithm that will maximize the variance, because the variance is one indicator, for one class while minimizing the variance for another class. It does the same, right? For one class, maximize, minimize, and from this projection, maximize the variance to the opposite class while minimizing the variance to the another class. This common spatial patterns gives us a very good discrimination. Okay, that solves this spatial mixing. And we will see the mathematical formulation of common spatial pattern. Just conclusion, in order to obtain good band power features, we need to apply some spatial filtering before even calculating log band power. And some research use tone imagination. This will also generate very strong suppression. Right, so you can control what to move forward by imagining right, back, left, with both foods into some directions, and tone plus BCI can be built. However, again, due to this balloon conduction effects, spatial smearing, it's still a very difficult task if you compare to P300-based BCI.